Barry McDonough is the CEO of Hinalea Imaging, which he co-founded in 2019. Barry is an experienced senior executive with a proven record of growing businesses across multiple industries and geographies. Barry.
Thank you, Jim, and thank you to Jason and to John as well for the opportunity to present here today. So I'm here to represent Hinalea Imaging. We are a Hawaiian-based startup. We have operations in Kapolei and in Emeryville in California. And today I'm here to talk to you about intelligent imaging. And it has some, reaffirms some of the themes that Isaiah was just talking about. So let me move on here. Okay, perfect. Okay, so the first question is what is intelligent imaging? So intelligent imaging has two parts. The first is a sensor, and this is essentially the sensor we're looking at here is called a hyperspectral imager. I'll talk a little bit more about that in a second. The second part is machine learning, and I'm acutely aware that there's a big buzz about machine learning and it's going to solve all of the world's problems, but in this specific instance, we're using it for some very, very key problem solving in the agri-food space. The three applications that we're targeting within agri-food are: one, maximizing yield; two, the quality of the produce; and three, the safety of the produce. And really what we do is we take this, through these intelligence imaging solutions, we generate rich data sets of spectral and spatial information relating to a particular target, and then we use machine learning, we train machine learning to solve a specific problem. So this is all about problem solving. Now, here's an example of what a hyperspectral imager looks like. When you see something, you see it in red, green, and blue. And I know that sounds a little bit unusual, but essentially we see in red, green, and blue, and everything, all of the colors in between are interpolation. The hyperspectral imager has a spectral resolution of about 100 times your eye. That means that it can see things that you can't see. You can also, whereas we see in the visible, you can also extend hyperspectral imaging from the UV all of the way out to the shortwave infrared and beyond. So here, this is an example of a color camera of a chip or a crisp, depending on what side of the Atlantic you're in. And you can see here that this is what we would see with our eye, and this is what most inspection systems would see in a food production facility today. The image on the right is what we can classify with a hyperspectral imager. And all of that little data there, I think if I can point here, that looks a little bit like lava. Does anyone have a guess of what that is? That is the seasoning on the chip, on the crisp. So for this particular company, they were very interested in having a quality control metric to determine what the seasoning of their chips was. So we could do this in real time on a production line, measuring hundreds of thousands of crisps as they move down that production line. It's seeing things that we can't see with current vision systems today, and then training them to solve a specific problem. So if this fell below a certain level, then they'd be able to go back upstream and add more seasoning. So this is just an example of the hyperspectral imaging sensor that we use. The next component is the machine learning part of this. And, you know, to be very honest, you know, this is a black box, as Isaiah said. This is a black box. I could not explain to you what happens in the middle here. But what I do understand is that it's a process of training. And if you put the right input in, you get some pretty phenomenal results on the way out. And what you have to do is you have to go through a process of, with our particular system, we go through this process of ground truthing. So say, for example, with strawberries, the measure of the soluble sugar content of a strawberry today is arrived through using something called a Brix refractometer. And it's a very proven technique. Sorry. It's a very proven technique for doing that today. What we do, and we're working with one of the largest berry companies in the US, is we have been taking ground truth data of thousands upon thousands of different types of berries, blueberries, raspberries, blackberries, etc., and strawberries. And then we match them with the images that we see with our particular sensor. And then we go through the process of building up an algorithm so that all of that can take place automatically. So the Brix refractometer, which involves, it's a mechanical test where you have to take the berry, you have to crush it, and you have to stick your probe in. Now you can actually do this in line with this inspection system, so that as these clamshells of berries are moving down the production line, you get a real-time view of the ripeness of the berries, the aggregate ripeness of the berries in that particular clamshell. And that then means that this can all be automated, and they can be routed to West Coast, East Coast, North or South, depending on that freshness, so that we don't get that horrible mold that you see after a few days in the berries that nobody likes. So it's this process of taking all of this rich data that we're capturing and turning it into intelligence to solve a specific problem. So the sensor and then the machine learning. The next question is, well, why is this happening now? Why is this technology important today? And again, I'll add to something that Isaiah said or confirm. This hyperspectral imaging technology is not new. It's existed for decades. But what has changed has been the cost of it. So it's been predominantly used in military and mining applications because the systems themselves have cost hundreds of thousands of dollars. Today, that cost has gone from hundreds of thousands of dollars to thousands of dollars en masse. And that means the applications that you can use them in have increased. Also, at the same time, they used to be very, very big, bulky systems. Now they're systems that can fit in the palm of my hand. So I can put them and use them in many, many different applications. So the hardware, the economy and the flexibility of the hardware has improved. At the same time, the suitability of the software, the suitability, the accessibility of this machine learning technology has improved at the same time. So we have access to all of these machine learning resources. We have access to all of this new improved computing power so that the vast amount of data that is generated by these systems can be converted from data to intelligence in real time. And then you can make decisions operationally based on those. So you have this convergence of a reduction in cost coupled with this improvement in computing power and access to machine learning that's leading to all of these opportunities. So what does this mean? Where are the two key areas that this technology is being used today? One is an upgrade of current spectral inspection technologies, whether that's a normal camera or a spectrometer. And then the other is transitioning lab-based inspection solutions to the field. And I'll give you an example of both, a case study of both of these in the instance in a second. But on the left-hand side, this is essentially taking tests that you could not do before using normal, the existing vision system technology. And then on the other side, this is taking tests that would typically go out to a lab, but doing them in the field. So think about maybe you're checking for pathogens in a production facility. You take your sample, it gets incubated, it goes out to a lab. It comes back, and maybe 48 hours later, you determine whether you have a problem. This is doing this real time in a production facility. And the supply chain implications of that are really quite enormous. So there's this technology, Hinalea focuses on the food quality and the food safety side of this. It's been used in industries, many other industries, semiconductor, industrial, defense. We focus on this space, but our core technology has been taken by our partners into other industries as well. So I'll talk a little bit about, I mentioned earlier on the three areas that we're focusing on. So precision agriculture. Earlier, Isaiah talked about hydration levels in fields. We can also look at things like plant health, detection of weeds, detection of diseases, and also using it to optimize harvest. It can be used on space systems. There's systems in space. There's systems in planes. There's systems in fixed-mounted stands in fields. There's systems on tractors, or you can go out and have a portable system yourself. We're also then working in food quality. It's been used in things like ingredient uniformity, product uniformity, the freshness and the grading measuring all of these metrics, and it really just depends on where there's a problem that we're looking to solve. And then lastly, and I think this is one of the areas that will have the biggest impact, is safety. So the safety of foods. We're working with the USDA in a CRADA agreement to try and bring pathogen detection into facilities. We're working with other large industry partners to do things like aflatoxin detection in the field. It's improving the safety and the quality of our foods. Okay. And I'll talk about some of these case studies. So this is an example of one of those particular case studies today. So aflatoxin, as you may know, this is a toxin it's a fungus-based toxin. It develops on things like grains and corn, and it can make people quite sick and cereals, and it can make people quite sick where it's found. The standard testing today for aflatoxin is an assay-based test. And essentially, it's like a little science project. You have to have all of your tubes, and you take the specimens, and you ground it up, and you put it in solution, and you put the strip in, and then after about 20 minutes or so, you'll come up with an answer. Very time-consuming, very, very costly, and also prone to error as well. But it does have error from a human perspective. It does have good accuracy and has been shown to do that. What are we trying to do? We are trying to do with this intelligent imaging, we're training our system to be able to detect aflatoxin from a visual perspective. So we take lots of samples of whether it's nuts we're looking at or grain with varying degrees of aflatoxin, and we train it to be able to pick up and distinguish between those. Both these systems today, our solution and the assay-based tests, they typically work at about 20 parts per billion. The advantages of having it, this is what the actual system looks like in a facility, and you can see a little drawer here. You put your Petri dish in with the sample, it images it automatically and gives you a result back. That's all you have to do. There's no other requirement from a technician operating this. So you get that increased speed to answer. It's automatic. It's usually anywhere between 20 to 30 seconds. You get a reduced cost because you don't have to have a technician running this all the time. It's completely automated other than putting the sample in. And there's reduced opportunity for error in that you don't have a technician making a mistake in terms of that process of analyzing the sample. And then lastly, and this is one of the areas, is that this is a very specific test. So if you're using an assay-based test for aflatoxin, you're only using that test for aflatoxin. With intelligent imaging, you can train the system to look for many, many different things all at once. So in the same time that you're looking for aflatoxin, you can train it to look for the hydration of that particular nut or mechanical defaults on that nut, and all of these different things all at once. So it gives you that move from very specific testing to a broad set of testing criteria. So this is another example of where intelligent imaging in general can be of value. Another one, and sort of mentioned this 5 minutes. Okay, thank you. Mentioned this already, was the measuring berry quality. So Brix ratio is essentially the standard for the level of soluble sugar in a strawberry. Typically, you want that above 8, and that's something that is used today. I'm using this Brix acid refractometer. It is a very involved process, as I mentioned. Mushing, you take your sample, you crush the berry, you put the probe in. The problem with doing that is that your sample no longer exists. So you're actually taking your product, and every time you want to sample something, you're going to destroy it. So you end up doing very, very small levels of sampling because of this. So the idea and what has been done is you can move to spectroscopy, and that looks to automate this a little bit. But the challenge with spectroscopy, while it's good to measure the Brix, it doesn't actually measure the acid component of this. And I probably should mention, Brix acid is actually whereas Brix is the soluble sugar, Brix acid is the accepted metric for essentially the overall ripeness of a strawberry, so the consumer acceptance of that. So you can't get that today with a spectrometer, whereas you can train a hyperspectral imager for that. You can also train that imager to look for things like firmness or shape or mechanical damage on that strawberry. All of these things in one. And that means that you get this fantastic breadth of inspection where you can look for many, many different things, not just the quality, but also the food safety side of this. And then secondly, then you get this scope of inspection rather than it being a very, very small sampling exercise whereby you're measuring maybe, you know, a 0.1% of probably not even that, a 0.1% of your input. You're able to essentially measure everything in line as it's going in and use it also for supply chain optimization. So that is the sort of a second example of where this technology is being used. And then lastly, how these systems are deployed, it really varies depending on the problem. It can be anything from, you know, a portable lunchbox-sized system that you bring out into the supply chain. It can be a system that's going up to space. It can be UV. It can be an inline production system. It really just depends on what you're looking to do. That's how the hardware is done. And then the algorithms are typically managed then from a cloud perspective. So a key part of this, and Isaiah also mentioned is keeping those algorithms up to date. So you have a growing season, things can change over time. So you have to have this process of constantly reaffirming your data set and updating that so that you can take any of those key learnings and then incorporate them into your algorithms as well. So this is typically, it's a two-part component. It's the hardware to do the sensing. It's the algorithms to take that data and move it into intelligence. So that is just sort of the quick introduction to intelligent imaging. It's got lots of applications. It's a new industry-level technology that's been rolled out today, and we're happy to be a Hawaiian company involved in it.